Okay, so welcome everybody. Happy, proud to have here today with us, talking to us, RIDA LARAKI, a researcher and a director of research at CNRS, an honorary professor at the University of Liverpool, and an associate editor of the Journal of Dynamics and Games, International Journal of Game Theory, and more, and an energetic, lively fellow and friend. RIDA, the stage is yours.
Thank you. I feel to be with my family today, so I'm happy to see all of you. So it's sorry, there's something. So it's a paper who started, with an essay in honor of Sultan, 75th birthday, by Roger Myerson. So he wrote an article, an essay, Sustainable Equilibria in Culturally Familiar Games. So let me just thank my co-authors, Ari Govindan and Luca Pal. I think Luca might be with us. It was a great pleasure to work with them. Very great minds, both of them. And Luca is now, after his PhD in Rochester, he's now joining the University of, so in Bonn. He's in Bonn postdoc with Sven Radi. So sustainable equilibria. So Myerson wanted to define some criteria for refinement of equilibria. One of them is one of them will be one of them. So the set of refined. So sorry, I have a problem with my screen. So he wanted the set of refined equilibria should be a non-empty. I'm sorry. So he wanted the set of refined equilibria to satisfy some properties, such that non-emptiness, such that invariance to transformation to properties, to some properties. And so for example, in the Battle of the Sexes game, he wanted the two pure strategic equilibria to be sustainable and not the mixed equilibrium to be sustainable because of some cultural familiarities in the games. He dismissed some refinements that may not select the mixed equilibrium, such that persistence equilibria, which fail invariance, and the ESS, who fails existence. And then he tried to give some idea, some mathematical idea of having sustainability using fixed point theory, and in particular, he gives this intuition from fixed point theory. So if you take a function from -infinity to +infinity, which is a generic function, it will cross the x-axis an odd number of times. Each time it's positive, it will be called a +1 index cross. If it's minus, it will be, if it is decreasing, it will be a -1 cross. And the sum of crosses will be, so there will be an odd number of crosses, and the sum of the indices will be +1. And then, so there is a link with the fixed point theory. So if you take so it just you do some kind of you turn the map, you see, by compactification, and you take a fixed point. You look at fixed point of a function, which is the crossing the diagonal. You have exactly the same phenomena. So there is a link between this result, this intuition of Myerson, and fixed point theory. And then Myerson conjectured that somehow this index, so there should be a way to define index for equilibria in games, and there should be a way to assign +1 index to sustainable equilibria and the -1 index to unsustainable equilibria. So this was the intuition of Myerson. And in fact, what is amazing is that Myerson was seemingly unaware that there was a theory on that, on index of equilibria already at that time by Ritzberger and Gould-Pierce and Sacchetti. So Ritzberger, he defined index for components of equilibria and not only for generic equilibria for generic games. So you can define index for equilibria in games using fixed point theory. And now there is, if you are interested by this topic, you should look at the book of McLennan, which is really the great book on this topic. So it's a very advanced group on fixed point theory. So if you're interested, just look at this book. And then Meyerson concluded with this open problem. Somehow he recognized that he didn't define sustainability in a very formal way, and he was hoping that one day there would be some kind of breakthrough to, some kind of theory that will prove his statement. And so Joseph Hofbauer formulated later sustainability for a generic game and provide some conjectures. One of them will be the one which we're concerned with today. So Hofbauer formulated the Meyerson's criteria as follows. He wanted strict equilibria to be sustainable. In the battle of the sexes, he wanted only strict equilibria to be sustainable. And if a game has a unique equilibrium, he wanted to be sustainable. Also, in every generic game, he wants that in every generic game, there is a sustainable equilibrium. So this was in Meyerson, and also sustainability should be something invariant to the addition and removal of inferior replies, which is what we saw in Meyerson's requirements, and something nice that, so sustainability, this is important. Sustainability should be invariant to addition and removal of inferior replies. So this is a kind of independence of a relevant alternative condition. What is an inferior reply? It is a strategy which is not a best reply to the equilibrium. So if I add strategies that are not best reply to equilibrium, if I remove this strategy, then I want the set of sustainable equilibria to be stable, to be doesn't change. So this leads, so this is a strong axiom. For example, if you apply invariance to this IIA condition to a game where there is a strict equilibrium, you remove all other strategies because they are not best reply to the strict equilibrium. You have a game with only one profile. And because of existence, you want existence of every game. This implies that this strict equilibrium should be sustainable. So then Hofbauer moved on and defined an equivalence class among equilibria.
May I ask a question now, or shall I wait till the end of the talk?
Perhaps you can wait, perhaps, if you...
Okay.
If the talk has an end.
It's not clear, yeah. So Hofbauer defines an equivalent relation among pair G and sigma, where G is a game, sigma is an equilibrium of the game. So a pair G sigma will be equivalent to a game G hat sigma hat if I remove all best replies to sigma in G and sigma hat in G hat, I have the same game after relabeling of strategies. Okay, so clearly if you have IIA condition, games which have the same in the same equivalence class should have the same sustainable equilibria. And if you combine A5, which is IIA with uniqueness, if there is uniqueness, then there is sustainability. Then if a game can be made unique in an equivalence pair, then it must be sustainable. And what is the ingenious idea of Hofbauer is to add some kind of minimality and define sustainable equilibrium as an equilibrium of a game sustainable if there is an equivalence pair in which it is the unique equilibrium. Okay, so that's the definition of Hofbauer. And let me give an example in the battle of the sexes. So in the battle of the sexes of Meyerson, so you have two equilibria in red and strict equilibria in red, and there is one completely mixed equilibrium. Let's show how this strict equilibrium can be made unique. So it's very easy. Just you add the strategy X and strategy Y to both players. You see that X is an inferior reply because it gives a strictly smaller pair if L is played, and Y is an inferior reply because it gives a strictly lower pair if T is played. So but these strategies are here to kill strategy B and R, which now becomes strictly dominated by X and Y. If you eliminate B and R, then we can eliminate X and Y, which are now strictly dominated by T and L, and we have a dominant solvable game with a unique equilibrium, which is TL. Okay? So this implies that this strict equilibrium is sustainable. And as we are going to see at the end of this talk, you will conclude that the mixed equilibrium is not sustainable. So this means that you cannot add strategies to the player that are inferior replies, such that the unique remaining equilibrium is the -1 equilibrium, which is we'll see later, this has a -1 index. That's why it will not be sustainable. So this is in line with Mersenne requirement in this game. If you take this definition of sustainability, then we will have solved this problem of Mersenne, at least for the Battle of the Sexes game. Now let me take an example where the sustainable equilibrium is a mixed equilibrium. So here it's a coordination game. So the diagonal has 10 payoff and the rest has 0. So there are completely 3 strict equilibria in the diagonal in red. 1 completely mixed equilibrium, 1/3 for each player, and 3 other mixed equilibria where player mix uniformly between 2 of the actions. So what is interesting is that the completely mixed equilibrium is sustainable. How? So it's not easy. So it's a construction that you can find in the pages of schemed. You can add 3 strategies X, Y, and Z, which are inferior replies to the completely mixed equilibrium. And in this bigger game, there is a unique equilibrium, which is the completely mixed. And 3 other equilibria, mixed equilibria, which has support 2, does not have this property. Okay. So now let me state more formally the Mersenne-Bauer conjecture. You have a set of players n, so notations, general notations for this talk. For every n, a finite set of pure strategies, set of pure strategy profile S, as usual. Sigma n will be the mixed strategy profile for player n. The set of mixed strategy profile, 1 for each player, is capital sigma. So standard notation S minus n, sigma minus n, if for players other than player n. You have the payoff vector function, which goes from strategy profile to r to the power n number of players. So the component small n will be the payoff of player n. And you have the space of game where payoffs vary, which is r to the n cross s. And the equilibrium correspondence will be denoted by E. So G sigma is in E if sigma is an equilibrium of G. So now index of equilibria. If G, take a game G, I take U be a neighborhood of sigma in Rn to the r to the power ns, and take a differential map F whose fixed points are G, and F is a function, in fact, implicitly is a function of the game, and we want this function to move continuously with G. One possible function is the function that Nash used in his PhD to prove existence of equilibrium. So this is called, in general, this kind of map are called Nash maps. So take a Nash map, but take the displacement map of which associate to a profile of strategy sigma minus F sigma, and call sigma regular equilibrium if the Jacobian of the displacement map at sigma is non-singular. And if all equilibria are regular, then call this game regular, and assign an index +1 or -1 to an equilibrium if the sign of the determinant of the Jacobian is +1 or -1, is positive or negative. And what is important to note is that the index is independent on which map F is used. Okay, independent on the Nash map. So this is a topological invariant. So this was posed by De Michelis and Germano. And now what is the Bauer-Mersenne conjecture? It says the following: a regular equilibrium is sustainable in the sense of the definition above of Bauer, if and only if it has index by +1. So this sustainability concept will separate equilibria between the good one, the +1, and the bad one, the -1. So it's between refinement and selection, because refinement will say nothing here. In fact, it's kind of selection theory. We try to select an equilibrium for every game. Here we don't select one equilibrium, we select a set of equilibria, the one having +1, so it's half of the equilibria somehow, and we ignore the -1 somehow. So it's not exactly refinement, it's not exactly selection, so it's kind of between. So this was proved by von Schiem and von Stengel for 2-player games using very sophisticated tools of polytopial geometry. But this kind of proof, we don't think it will work for n-player games. So this paper, so what I'm going to present today is the proof for the conjecture for n-player games, and it will be mainly using algebraic topology and some kind of differential topology, but only for algebraic sets. So since we know that the sum of indices over all equilibria is +1, this implies that any regular game has a sustainable equilibrium. And also, since the set of regular game is open and dense, it implies that almost every game has a sustainable equilibrium, which implies that we have the requirements of Meyerson, except the A3. A3 says that if an equilibrium is unique, whether it is regular or not, it is sustainable. But our proof, in fact, works for not only for regular equilibria, it works for isolated equilibria. So our theorem is an isolated equilibrium is sustainable if and only if it has index +1, which implies that if an equilibrium is unique, then it is sustainable. And has index +1, it is sustainable. And so if it's unique, it must have index +1. And since it is isolated because unique, it must be sustainable. Okay. So we have now all the requirements of Meyerson for regular game, for games that are generic. So in the last section, which is new stuff, which is not in the paper, which is available, I will speak about extension to non-generic games. So the proof, there is an easy part. Take sigma be a regular equilibrium of a game. Now suppose that G sigma is equivalent to a pair G hat sigma, where sigma is the unique equilibrium of G hat. Now delete all inferior replies to sigma, and this gives us again G star. And this is a very nice property of index, is that if you drop inferior replies, you don't change the index, which implies that the index of sigma in G is exactly the same as the index of sigma in G star. And similarly, if we delete the strategies from G hat, we have also G star, and this implies that index of sigma in G star is equal to the index of sigma in G hat. So all the three indexes in the three games are the same. But since sigma is the unique equilibrium of G hat and the sum of indices of equilibria is +1, it must have index +1. And this proof works also if sigma is an isolated equilibrium, because it's from itself a connected component of equilibria, which is a singleton, and the same proof works exactly the same. Okay. Now, for the difficult path, the first observation for the difficult path is to observe that index, it uses the fact that index is equal to the degree. So what is the degree? So to define the degree, you should first consider the projection map, which associates to every pair G game and sigma and equilibrium. In the equilibrium correspondence, the projection in the first component, which is the game. So let me give an illustration example. So take the first figure. So here it is the space of game. In red, you have the equilibrium correspondence. We can orient the space of games. And from this orientation, we deduce an orientation for the equilibrium correspondence. And the Kohlberg and Mertens famous result in '86 proved that the equilibrium correspondence is homeomorphic to the space of game, and there is an homotopy of the projection map. So what is the projection map? So if you take a game is a point here, and if you look above here, if you look above the game, you have, sorry, if you look above the game, all the crosses on the equilibrium correspondence are the equilibria. So if I take the x equals 0, the cross here, I cross 3 times, so this means I have 3 equilibria. Okay, so three crosses, 3 equilibria in this example. And now what is the degree of an equilibrium? This is the local orientation of the projection map. So now we have an orientation on E given by the orientation in the space of game. And now if you follow this correspondence and we take a neighborhood of the equilibrium here and we project this neighborhood and we look at the orientation when we are moving in the equilibrium correspondence, then we go in the opposite direction than in the original, in the space of game. So this has index -1 here, okay? And the theorem, important theorem we are using here is from Govindan and Wilson, who proves that the degree is equal to the index. So what they prove, in fact, they prove that the degree is equal to the index of the Gull-Pierce-Sacchetti map, which is a Nash map. And by the theorem of De Michaelis and Germano, we know that the index is invariant with respect to which map is used. So this implies that degree is equal index in general. Okay. So now we are going to use a result from differential geometry, differential topology called Hopf extension theorem. So take G be a game and sigma a +1 index equilibrium. Take F to be the beta reply map in Nash PhD thesis, whose fixed points are equilibria of G. Since the sum of degrees over all equilibria is +1, and the sum of degree over all equilibria other than sigma is 0. So now what we can do is to modify the map outside a neighborhood U of the sigma and have a new map F0, which will be continuous on the strategy space. And we'll have only one equilibrium, which is sigma. And this is possible because of this theorem of Hopf, of extension theorem, which is the following theorem. It tells you that if W is a compact, connected, oriented K+1 dimensional manifold with boundary, and F is a function defined on the boundary and have values in the sphere, the K sphere, which is smooth, then we can extend F to all the space W, if and only if it has degree 0. Here, what's played the role of function F is not our F, so it will be the displacement map, which will have degree 0 on the boundary of U, and we want to extend it outside U, but on the rest, and having value on the sphere. The sphere will be R minus 0. 0 will be in 0, meaning that you have an equilibrium. So we don't have this map. We don't want to have any equilibrium outside the neighborhood U, and this is how we use this theorem. So let me illustrate this theorem in an example. Take this 2-player symmetric game, and we concentrate on symmetric strategies and symmetric equilibria just for illustration, because we'll have only 2 dimensions here. A symmetric profile will be represented by a number x in 0, 1, which is the probability of player 1 playing L and the probability of player 2 playing L. So we have 2 strict equilibria, which are playing L with probability 1, playing R with probability 1, or completely mixed 1/2, 1/2. So the pure strict have index +1, the mix has index -1. And the Nash map, can be computed like this, but let me show it in a figure. So this is the figure in black. It crosses the diagonal 3 times, which are the 3 equilibria in red. If you take this equilibrium with index +1, we can follow the map in green, which is our Nash map, be equal to this map on the neighborhood of the equilibrium, which is this neighborhood, which is x higher than 2/3. And from then we can continue the map such that we don't cross the diagonal, So it's very easy to do in one dimension here. You cannot do this for the mixed equilibrium. So if you cross here, okay, and here the value should be higher than 0, here the value should be smaller than 1 or equal to 1. If you are equal to this map here, and you should at some moment, if you are continuous, cross the diagonal, so you cannot make this -1 equilibrium unique, as you can see, okay? So this is the topological explanation of this result, why you can do it for +1 and not for -1. So now the difficulty is to transform this map F0 by adding strategies and mimic this F0 and have this as the result of a game. So how we do this? First, we should eliminate the dependency on player N strategy, because F0 now is a map which is dependent on all sigma, and not only on sigma -n, which is in general beta reply map, depend on what the other player is doing, and not for player N, and not for what player N is doing. So for that, we construct an equivalent game by just, this is a trick. We duplicate the strategy space. So we add a second coordinate to each player, which will be the strategy set of the next player to him. We have modulo N here. So the capital N +1 is player 1, and which will be irrelevant for him. But it will, so now we extended the game. We have now a bigger strategy space. And when a player chooses a strategy, so what we do is we use N-1 second coordinates of player N-1, the second coordinates of player N-1, which will be the strategy space of player N, and then we use the map F0 applied to this, and so we don't have the dependency on player N at all. But still, this function is not multilinear. So well, also we should do some kind of simplicial approximation of this function, multilinear simplicial approximation of this function. So what you want to do is to add vertex and to have a simplicial subdivision of the strategy space. Now we have 0, 1, which is the original strategy space. This is the duplicate strategy space, which is the strategy space of the player next to player 1. So now we have this space, we add vertexes, and we have a triangulation. And we want a particular triangulation. We want something called Delanois triangulation because of some nice properties of this function. What is a Delanois triangulation? So I will show you what is not a Delanois triangulation. This is not a Delanois triangulation. So if you have a k dimensional simplex with k plus 1 vertex in this triangulation, and we take the sphere, the k sphere, which connect this extreme point, we want this sphere to not cross any other points. So here it is not a Delanois triangulation because there is another vertex in the sphere. We don't want that. So generically, it is always possible to have a Delanois triangulation if you take general position point with respect to spheres in RD. So if C is the convex envelope of some k points which are not independent because D k is not the same. So k is much bigger than D. So we are going to add many points. So now to have the Delanois triangulation, it is sufficient to take to add a dimension and the Euclidean norm for each point xi, and take the lower convex envelope of D, which is the graph of a piecewise linear function rho, and each time this function is linear, it's defined a triangle which will be our Delanois triangulation. The difficulty in our case, and we have a very huge appendix working on this Delanois triangulations to show some properties we want. And the difficulty is that we are constrained to be in the space with many other constraints that we need to have. And it's not easy to have this general position condition. And all the difficulties to show that we can have a general position condition for spheres, which allows us to have this rho function, which will be important in our construction. And now the very difficult part, I will just, it's the smallest in my description, but it is the bigger in the paper. We have a sufficiently fine Delanois triangulation. All the vertices will be added as pure strategies. In fact, what we do like Van Stengel and Van Steen, we add strategies, we never eliminate any strategy. So III condition says that you can add or eliminate strategies and be stable. Here we are going only to add strategies. So we add several vertices which are given by the triangulation, the vertices of the triangulation, the Delanois triangulation. Then we are going, so these strategies, because they are duplicate strategies, because they are mixtures of other strategies, they have already a payoff given by G. And now we add to this payoff several components, very complex, lot of tricks, and most of the tricks, not all of them, come from Govind and Wilson paper on this characterization of essential equilibria in portion of National Academy of Sciences. And if you have never read this paper, go read this paper because it's a great paper. It's amazing, great paper. And many of the proofs we have come from this paper. And we are going to use the Delanois triangulation, the rho function in the Delanois triangulation as part of the bonus, but it should not be only the unique part of the bonus. And then we are going to use that F0 has only one fixed point to deduce that there is only one equilibrium, and we have a best replies function that's really approximate this F0, okay? So that's the general idea of the proof. Okay, so if you have any question, perhaps you can ask, and then we can move to the second part, which is extending sustainability, or we can keep questions to the end. Perhaps we can keep to the end, I don't know. So let me move, okay. So now it's something very important. Can we add, remove strategies that are best replies? Because we can add, for example, I can add a strategy here which gives to player 1 exactly 6, not more than 6, because otherwise this will not be an equilibrium, TL. But if I give him 6, it's still an equilibrium. So can we also add strategies that are not necessarily best replies? And eliminate strategies that are not best replies, meaning that somehow can we just restrict ourselves to the support of equilibrium and remove the rest instead of eliminating non-best replies, because sometimes some best replies are not in the support, but we should keep them when we speak about sustainability. So take this 3-player game with player 3 is somehow dummy. It has three strict Nash equilibria, TL, BR, which has index +1, and the one completely mixed with index -1. Okay. Fine. So this is a regular game, and everything is fine. So now what is amazing is that we can add strategies and get a larger game in which sigma will be the unique equilibrium. This -1 equilibrium will be the unique equilibrium by adding strategies. You cannot do this for two-player games. Why? Because in a two-player game, if you add new strategies and the sigma and equilibrium becomes the unique equilibrium, then sigma must be quasi-strict because of a result of NORD for two-player games. And this implies that the best replies are in the support of sigma. This means that all the strategies that I have added are necessarily inferior replies strategies, which means that I can never make a -1 equilibrium unique in a two-player game by adding strategies. But in three-player game, this is possible, and this is the example. So here, if I take the mixed equilibrium, 1/2 TB, 1/2 LR, each player one gets a pair of 3, player 2 gets a pair of 3. If player 1 deviates to capital B, he gets 3. If player 2 deviates to capital R, he gets 3 also. So we see that in this larger game, three-player game, so the proof of this, that -1 equilibrium is unique, it's 10 pages proof. So it's long proof. And so it's not in the paper. So if someone is interested by the proof, we can send him the proof or her the proof, okay? So there is nothing wrong because sigma, G sigma and G hat sigma are not equivalent because we add strategies that are not best replies to the equilibrium. So that's important to keep. And there is an open problem raised by this. Can any equilibrium be made unique by adding not necessarily inferior replies? So like here, we can add strategies that gives exactly the path of the equilibrium. So if you can add strategies to the player, any equilibrium can be made unique, not only +1, -1. So we have an example where -1 can be, but we think that this is true for all equilibria and whether it is generic game or non-generic game. So we give in the paper an example where the game is non-generic and any equilibrium can be made unique by adding players and strategies. But we don't know if it is true always. So now the interesting question is how to extend to, which is not in the paper of Bauer nor in the discussion of Meyerson, but I guess Meyerson wanted something which is true for all games, not only generic games, because most extensive form games are, when you put them in normal form, they are not generic. So we want also a theory which applies to also non-generic games. And so now what is the right definition, the right extension? So let me do a first attempt and first prove some small results. Fact 1, if you take a non-isolated equilibrium, then you cannot make it unique by adding inferior replies. So this means that our result is sharp. We show that an isolated equilibrium, which has index +1, can be made unique. But if an equilibrium is not isolated, you can never make it unique by adding inferior replies. Why? So suppose not. Then there is a sigma n, an equilibrium of the game G, which converts to sigma and sigma n. And then, since sigma is the unique equilibrium for the larger game where you added strategies that are inferior replies to sigma, sigma n is not an equilibrium in G hat, so there is a deviation by some player, and but then you can take a subsequence such that the player is fixed and the deviation, best reply deviation, is fixed, call it theta I. Then go to the limit. By continuity, theta I will be also a best reply to sigma in G hat, and so theta I is something that you added, and this is a best reply, and this is a contradiction that you add only inferior replies. So you cannot make an isolated equilibrium unique. Also, you cannot make a strict subset of an equilibrium component unique. So you know that in finite game, which was proved by Kohlberger and Mertens, so the set of equilibria is a union of, so it's a finite union of connected components. Each component is called an equilibrium component, a Nash component. And perhaps you can ask yourself, and you know that in general, in refinement, stable sets are subsets, strict subsets, maybe strict subsets of some connected components. So take a strict subset of a component and ask yourself, can I make it unique by adding inferior replies? The answer is no. Why? So if you can make it unique, then it must be closed because it will be the unique component of Equilibria of a larger game. So it will be not only closed, but also connected. But then since C, the component in the original game is connected and U is not equal to C, so you should have a sigma n conversion to sigma n not in U, but sigma n in C, and then you apply the argument you use in fact one to deduce a contradiction. So you will have a contradiction. You would have necessarily strategies are not better replies, and this is not good. So the unique hope we have is to make an entire equilibrium component unique by adding inferior replies. But then this is a big problem because you may have no equilibrium component that can be made unique because of this example of Hawk and Hurkins. So this is an outside option game. So you have an outside option, or you can enter the game, and the unique equilibrium in the regular, so the game, if you continue the regular game, which has finitely many equilibria, which have index +1, -1, and there is a unique -1 equilibrium, which gives more than the outside option, which implies that you have only two components of equilibria, one which index -1, which is enter the game, one which is the outside option, which has index +2, because the sum of indices should be +1. So none of them has index +1. And if you make a component unique, it should have index +1 in the larger game, so it should have index +1 in the smaller game, which is not true. So the unique hope is to make a +1 index equilibrium component entirely unique by adding inferior replies. But this is bad somehow because this way of defining or extending sustainability does not give us existence, which is somehow important if you want to have a theory which applies to every game. We can do a second attempt, and which will be an axiomatic approach, and which will be in the spirit of Meyerson and of Bauer. So let's now we know that we cannot have a single valued concept, so we need like in refinement theory. So here we are going to be close to refinement theory. So we'd like to select for every game a subset of Nash equilibria. So an example is to take all the connected components, and this will be the solutions. Each component is a solution. You know that in generic extensive for game, the payoff in each component is fixed. Strategies of the player can move, but the payoff is fixed. So this is the outcome of the component. So you have finitely many outcomes in generic extensive games. So the prediction is fixed. It is the outcome, but the strategy that leads to this outcome may vary. Okay, so you can think of a component like that. So now we want to have sets that we want to call sustainable, and we want them to satisfy some axioms. We want existence for every game. So we want every game to have a sustainable equilibrium. Secondly, we want independence of irrelevant alternatives, exactly as we had before. So if a set is sustainable for a game, it remains sustainable after adding or removing inferior replies. So this is so we want these two conditions. But also we want the following. We want that equivalent games have equivalent solutions. So here equivalent is exactly what, if you look at the paper of Meyerson, he was speaking about this equivalence in particular. If you add positive transformations of payoffs, if you add mixtures, duplicates, mixtures of strategies, then you will not change the solution. So we want equivalent games to have equivalent solution, which is also an axiom which is used by Kohlberg and Mertens, and most of refinement theory use this axiom as kind of requirement. And we want also something I will call robustness, which is also something very, very used in refinement theory. We want a set of, if a set is sustainable for a game, it is sustainable for every perturbation of the game, okay? So if you take any nearby game, it has a sustainable set which is close to our nearby of our original game. In particular, if I perturb and the perturbation is a generic game, then I want to have at least some sustainable equilibria close to my game. So now forget about what he did before. because the sustainable equilibria we had before, they have a definition. Now we are going to see that this definition will englobe the other definition, which will be a consequence. And of course, the proof we did before will be very important to prove that the result we are going to prove is also true. And we want to have minimality. Minimality means that if C is a correspondence to satisfy the axiom A1 to A4, then for every game G, phi of G, which are the stable sets in game G according to phi, will be also stable subsets of stable sets in P of G. So these are the this means that somehow what we want is sets such that if I want to satisfy the axiom, I need at least to have this set, call this set as sustainable set. I cannot have less than this set, okay? And the result tells us that a correspondence satisfies A1 to A5 if and only if it's associated to each game its set of Nash equilibrium components which has positive index. So this is so this result is not in the paper, the version of the paper circulating. So it's something where we were working on much more recently now. So we wanted to have this result. And the proof of this is, so it's very close to the proof of, so it uses some of the proof of Govindan and Wilson, because in their paper, they are speaking about, they are characterizing essential equilibria. Essential equilibria are components, so essential components are components which has non-zero index. So if you take a component with zero index, so what they prove is that there is a perturbation. So if you take a game, you can add redundant strategies. So so to using invariance, and then you can perturb the game such that there is no equilibrium in the perturbed game close to the components. So the components, the zero index component will have no close by equilibrium, and so it will not be robust to small perturbations. So we will never have a solution close by. So here the index is 0. So if you take an index, a component with index k or minus k is an integer, there is a very deep theorem by O'Neill in the 50s showing that if you take a game, if you take a correspondence, a fixed point correspondence, and you take a component of fixed points, which has some positive index, then you can always, and you take some points in the components, you can always, and you assign them +1 minus indices so that the sum is equal to k is positive or negative, then you can find the perturbation of the best response function such that you have exactly this what you want. In particular, if you have a minus k, k is positive now, minus k component, you can find the perturbation of the best reply such that you have exactly only -1 equilibria close by and no +1 close, you know? So this implies that this violates minimality. Minimality, if so that's the idea. So the idea is to use this kind, so perturbing best reply function would be easy, but this is not what you want to do. You want to perturb payoffs in invariant in games where you can add delete, duplicate strategies. But if you want to do that, you should replicate the proof of Govindan and Wilson to have this result. So it's not a trivial result, but it's implied that if you want to have these axioms, we need to it is possible because there is always a component with positive index, and only components of positive index will have this property. So if you look at the definition of Obawa, when he's speaking about uniqueness, it's kind of minimality. He's using minimality implicitly there. So here, just we take this axiom apart as an axiom. And for robustness, it's really, if you go back to Meyerson, when he was speaking about this cultural, if you take the Battle of the Sexes game, if he says that if you play this Battle of the Sexes game, symmetric game once, probably player will play the mixed equilibrium. There is no reason they play something else because it's the focal point. But if this is, you are in a society where you observe what other people did before and you play only once this game, but there is a past, then there is little evidence. Somehow it's not very stable to this, slice perturbations is in the mixed profile. What you see in the society will imply deviations from this equilibrium. So it is somehow unstable to, not robust to some kind of perturbations. And so this is this kind of, so he wanted robustness, Meyerson. He wanted invariance, he wanted IIA, he wanted existence and minimality. So we think that this is somehow the formalization of Meyerson's requirements. So that's what I wanted to say. And thank you very much for having me. And sorry for the beginning, because sometimes I don't know why, and it happens to me 4 years ago, when I start a seminar, I'm blocked and I cannot talk for 5 minutes. I don't know why. And it happens to me today, and I don't know why it happens. So this is something that happens to me sometimes, so sorry about it.
Are there questions, people?
Can I ask a question? Can you hear?
Yes. Ah, Ritzberg is here.
Hi, Rita. How are you doing?
Thank you. Yeah, hi.
So going back to the last part where you talk about components.
Yeah.
You couldn't make up an alternative concept that says, take a union of components whose index, the sum of indices of the components in the union is +1. Ah,
okay, that may work.
Yeah, that may work. That could be a sustainable set, right?
Yeah, you can make them unique. You can make them unique by other strategies, probably. But we don't have the proof for that, huh?
Right, but it seems like something that could work, right?
Yeah.
Because then you actually get index +1 and not just positive indexes in your last result.
Yeah.
Okay. Yeah. Thanks. That's what I wanted to ask.
yeah, thanks. Yeah. So perhaps I can just stop the sharing so I can see people really. So someone wanted to ask a question at the beginning. So where is the person? Is there any question in the? Yeah. Yes, Galit.
No, I don't have a question. I wanted to ask whether there are more questions.
Yeah.
No more questions.
No more questions. Yeah.
Okay. If you have any questions, people feel free to unmute yourself and ask. None. Okay. Then anybody? No. Okay. Then Rita, thank you. Thank you so much for this talk.
Thank you. Thank you for asking me. Yeah. I stay if someone wants to ask a question privately.
Sure.